Okay, so welcome everybody. It's a great pleasure to have Rajesh Gopakumar, who's going to tell us and educate us on deciphering AdS CFT. So many of you have been to this lecture series before, so you simply should unmute yourself and ask questions, and otherwise keep yourself muted. The recordings of the lectures will be uploaded immediately on YouTube. And also there are the slides of these also will be made available on the website. One operational announcement is that the next lecture is not going to be on Thursday, but it is going to be on Friday, which is 23rd at 3 p.m. So that just adjust your calendars accordingly. And that's about it. So Rajesh, please take it on.
Yeah. Thanks, Ananda and Parthiv, for inviting me to this series that you folks are organizing. It's very good that there is this set of lectures for especially for younger researchers. So I have, keeping that spirit in mind, I decided to mostly do it like a Blackboard lecture, so to say, on the iPad, and the pace is also will be determined by the audience. So feel free to stop me whenever, and we can just have a informal sort of discussion. So that's the whole idea. And I may not always give all the details of everything, but if people are interested, we can discuss more of that. So, so let me first give the broad plan of the lectures. So roughly speaking, like in the abstract that was given, I will divide it into two parts, the lectures. The first part will be on a sort of will be a little broad brush and big picture, and it is about the strategy for deciphering or deriving AdS CFT. So we'll start with the how and the why of this topic, and then I will try to outline some broad elements of the picture, how you can go starting from the string theory, go to the field theory, or vice versa from the field theory to the string theory. I think certain broad elements which I think are now becoming clear that they are part of the final picture for a general understanding of gauge string duality or AdS CFT. So, but this will be, as I said, a quite broad brush and very a little schematic, but we can go into to some detail depending on the interest. And then the second part will be more concrete and will be based on recent work with Matthias Gaberdiel on concrete way of implementing this earlier strategy in the context of free n equals to 4 super Yang-Mills theory and its dual, the AdS 5 times S5 string theory. And so here I will talk about firstly a simpler, I will say how the proposal here is some kind of a generalization of an earlier proposal, the work on AdS3 with Lawrence Eberhardt and Matthias. So there in the tensionless limit of AdS3 times S3, we had made a proposal which by now we understand many aspects, including the matching of the spectrum and correlators. We understand in multiple ways, and in particular, a twistorial formulation of that sigma model will be very key. So I had given references to both my lectures at KIAS as well as Matthias's lectures at the pre-strings conference. And so I will only touch upon the ADS 3 times S3 story very lightly, but try to, so that was the motivation. So in a way, the template is the ADS 3 times S3, but if you have not really seen it, we'll go directly to the ADS 5 times S5 case. And here, things are still very much being developed. We have a proposal for how to quantize the sigma model, which is again very much uses the template of ADS 3 times S3 and fits in with a number of other things. So this proposal for the quantization of the sigma model gives rise to a spectrum of physical states, and we'll show that this is equivalent to the spectrum of planar super Young-Mills theory. So I don't know why this so this will be essentially the second part of the talk, and of course I'll say some, maybe if I have time, I'll say some words about future directions and the generalizations, and I'll also try to connect parts of the second parts of this concrete case with the broad picture of the first part. So that's the basic plan of the lecture. So let's start. Like I said, I'll try to make it like a Blackboard talk, so please stop me. So we'll start with the sort of the why question. Why is it important to derive or the gauge string correspondence or AdS CFT. So firstly, I should say, I mean, all of you know that the AdS CFT correspondence is sort of been the engine of progress in many areas of theoretical physics, and in particular quantum field theory and string theory in the last 2 decades or more. And it has had multiple impacts in different areas. And therefore, in a sense, the AdS CFT correspondence is a very central topic. I don't need to emphasize that importance. But why is it important to derive it or decipher it or decode it? Firstly, let me give a non-reason. A non-reason is not out of some mathematical rigor or trying to prove something for the sake of proving it. I think there are very good physics reasons why we should try to derive or prove the AdS CFT correspondence, because I think that's a real gap in our understanding. And and this is where, in fact, the how question will enter. If we learn how to, in the process of deriving it, the way in which we derive it, how we derive it, will actually teach us, I think, many things, many physics lessons. And this is why I think that's so the physics is the primary motivation, not some mathematical rigor or something like that. So this is why, in fact, the how question will also be important, and we'll talk about that. But let me spell out some. So that was a non-reason. Let me spell out some broad reasons why it is important. Firstly, it relates string theory to string theory to quantum field theory in a direct and surprising manner. So But what I really mean to, I mean, all of you know this, but what I mean to say when I give this as a reason is that string theories, as we have learned, and those of you who are studying the subject, when you come to it, you realize how powerful and amazing a framework it is. But it is as yet something which hasn't had made connections with tangible experimental realizations in nature. But on the other hand, quantum field theory is one of our best frameworks to understand most complex phenomena in nature, and it is extremely successful, and it is applied not only in high energy physics or particle physics, but in condensed matter physics and statistical physics and numerous areas. So quantum field theory as a framework is something, of course, very, I mean, it's one of our pillars of our understanding, and the AdS CFT relates these two in a rather non-trivial and very amazing way. So in trying to derive AdS CFT, we'll really, I think, what we can hope is that we get a window into how strings are part of nature's description. So this is a sort of a broad, kind of a very broad philosophical reason, if you wish, but I think it's a very important one, because it's the first clue we have gotten that the framework of string theory is very natural. It just is the same as quantum field theory, but in a different way. So it's an equivalent description, at least for a large class of quantum field theories. So the second reason is, of course, that it gives us an understanding of what quantum gravity is beyond it potentially tells us what quantum gravity is, of features of quantum gravity away from the GR limit. So and we can extend this both in the stringy features as well as the quantum aspects. So in some ways, this tells us about both. And of course, this is for AdS spacetimes, but by having a derivation, we can hopefully learn about, but probably there are general lessons here. So that's another reason, and by deriving it from quantum field theory, by decoding this hologram, I think we effectively can learn about that. And finally, and this is sort of related to the first point in some sense, but independent in some sense of it, which is that it gives new insight into strongly coupled quantum field theories. It tells us that there are many features of strongly coupled quantum field theories that we haven't really understood. There's some kind of universality in many ways about it, and we have few tools to understand that, and probably the bootstrap, which is the theme of these broad lecture series, is one of the few tools that we have, but that's also something very much to be developed. And so to have something systematic to understand and give a new perspective on strongly interacting quantum field theories is very important. And and I think this is one way in which, as I said above, string theory can connect to the real world and perhaps experimentally accessible systems. And people have tried this in the context of this ADS, CMT, or condensed matter systems, but there one has to make several leaps of faith that this is applicable indeed to sort of strongly coupled systems. And we don't know the reliability of these approximations or guesses that we are making. So understanding systematically, which is what the derivation would help us to do, I think can help to address these questions in a systematic way. So these are, of course, very ambitious reasons, but to really but to really achieve these, and I mean, if you ask many people their reason for studying AdS CFT, they'll usually give you one of these three reasons that I listed above. In a way, this has been there for 20 years, but I think we have still not made adequate progress in realizing the promise of AdS CFT, and I think that's because there are certain limitations we are that we are currently sort of facing in our understanding, and I just want to sort of highlight those. So the first one is that we only know a class of examples and mostly with SUSY. Supersymmetry, and so we know only a class of examples of the AdS CFT. So we don't so we don't have a kind of a general general prescription for understanding let alone general quantum field theories, but even large N conformal field theories, we still don't have a systematic way to obtain them. So the examples we have, these examples are from top-down constructions. From D-branes, and that's sort of the way in which Maldacena originally arrived at this correspondence by taking the near horizon limit, as I will mention later. So we, whenever we come up with some clever brane construction, we can try to see what, and we have a supergravity description of that brane construction. We can try to understand what the dual theory is, but this, I mean, yeah, this is firstly done with things with large amount of supersymmetry typically, or you have to make some guesses. So we lack a systematic way, as I said, to even generate a systematic way to obtain the bulk dual, the dual string theory. To a general large N gauge theory, for instance. For example, even QCD, or large N pure Yang-Mills theory. We don't have a way in which we can even make a good guess for what the dual string theory is like. So this is clearly a limitation, and we have been functioning in this limitation. And of course, we have been exploring, I mean, the large class of examples that we know is very rich and tells us many remarkable things. So we have been, of course, people have been have learned a lot through looking at these examples, and that's obviously useful. But if we want to go beyond that, I think we have to break out of this limitation. So even in these examples, so even a second limitation is like further kind of even further, and even in these examples, we are in a very narrow, we are mostly under a single lamppost, as I like to put it. And this is the large N regime. Of course, that's fine. That's perhaps still livable. But of ultra strong coupling, so in other words, the what is called the 't coupling is much greater than 1. So and this corresponds to the supergravity plus alpha prime corrections. So another way to say it is that the string length is going to 0, or the string tension is going to infinity. That's the regime where we have control over the theory. And this, of course, has been remarkable in that we have learned that gravity tells us a lot about strong coupling dynamics. There is something universal about strong coupling dynamics, etc. But we have been mostly under this lamppost, and this is sort of the figure that, in fact, all the nice computer-generated figures are by Pranavesh, my student. So I used to have a little caricature of this, but he drew it nicely. So we are, so if you wish, in the parameter regime, which I've shown this to in many talks, I think, before, in which you have a vertical axis which measures the strength of the quantum coupling, the quantum effects in string theory. So the vertical axis is are the quantum effects, and the horizontal axis are the stringy effects. And so this lamppost here is where the 't coupling, or the stringiness is minimal. That's alpha prime goes to 0 limit, as I said, and it becomes more stringy. The vertical axis is the, as I said, the Yang-Mills coupling, or the the string coupling, which is related to 1/n, and measures the quantum stringiness, the quantum effects in the string theory. But this, if we even restrict to the planar limit, large N, even here we are only in this corner of the parameter space where the stringy effects can be essentially neglected or included in alpha prime corrections. Whereas there's this whole region where the coupling takes an arbitrary value, and that is relatively unexplored. So we are mostly being boxed into this region of the parameter space. And so that's why in some ways it does not shed light on quantum gravity in the stringy or the quantum regime. So except maybe through hints like the Ryu-Takanagi formula, etc. So we have not been able to we have not been able to sort of to draw too many lessons. About either the stringy gravity or the fully quantum gravity. So this is why one of the reasons I mentioned earlier that has still not been fully realized. And relatedly, and the converse of that statement in the gauge theory is that we have not been able to access order one, coupling lambda of the gauge theory. So the intermediately strong coupling theories, which is where most of the strong coupling phenomena that people are interested in real life would be, we have not been able to learn much about that. And why is this? This is because we have not been able to quantize string theory. On AdS 5 times S5, even for even in the sort of classical limit of string theory, the genus 0.
I have a question here.
Yeah, sure, Anna.
Yeah, so my question is that, so before this duality, we were aware of one duality, which is this wave particle duality. And sort of the quantum mechanics was the formalism which naturally inbuilds the duality into the description, right?
Yeah.
So do you think there should be one such, does this, firstly, your approach or this thing, will it tell us anything about a duality invariant formalism? And because many things happen in the duality invariant formalism, which is not available in either of the limits, right? So can you share some thoughts on that maybe?
Yeah, no, it's an interesting thought. At the moment, this seemed to be very different. The string theory framework and the field theory, but in some way, what I think what one is seeing, at least in the examples one understands, is that it gets tautologized. The connection becomes tautological in some ways. In some limits, at least, you see that both sides are really the same, and there are different ways of framing the same object. But I think to be able to come up with something which is more duality invariant, I think will require us to really understand what is it that we are really equating. In some ways, we need to sort of. I think we are even in the earlier step where we guess that there is a wave particle duality, but we don't even have any real idea why waves and particles are really the same. So we can't even, so yeah. So I think the way to, unless one has some brilliant leap of the imagination, like in quantum mechanics, we may not be able to, I think we will only be able to address that question once we make some progress in seeing why the string theory is dual to the quantum field theory, in the sense that right now there are two well-defined frameworks. Quantum field theory is a complete framework in itself, and similarly, similarly, string theory, perturbative string theory, is a relatively well-defined framework, and it's a statement of equality of these two frameworks. And maybe there is a way in which these two frameworks can be embedded in something bigger. But it's a little different from the wave-particle duality, meaning there we realized that each of the frameworks we had was a little bit incomplete. Here we don't really see so then there was a need really for something that would complete both of them. Here it's not quite like that. It is quantum field theory, as far as we know, is a completely well-defined framework in itself. So there is so this is, but at the same time, I think there may be a framework in which the duality becomes manifest. And by what I meant by tautologizing the duality was sort of doing that. But there may be, once we tautologize it, we might be able to see why they are really, they're manifestly equal. So there's, so in a way, yeah, the attempt here is to make the two sides manifestly equal. Manifestly.
So the intermediate regime you were talking about, in such a formalism, it will be able to, one would be able to address the intermediate regimes much better way than, because here now we have.
Hopefully, I mean, that's still a long way from that at the moment. It may not, I don't know how analytically tractable it will be, but this other lamppost that I will be focusing on right now, which is of perturbative quantum field theory, by making the equality manifest here, one may be able to see how to kind of push this further. But yeah, it may well be that we have this other lamppost and this lamppost, and they are connected in principle, but we are kind of still this thing. But my basic optimism is that by understanding things around this corner, we will be able to push things, and then we'll have to see how it works. Yeah, so I'm just optimistic that we'll learn more this way. So in fact, there's the talking of the intermediate regime. I think I should mention that when we say order one coupling and so on, there is an exception, which is except in the case of integrable, except using integrability. At least for certain maximally supersymmetric theories, people have used integrability to go more into this intermediate regime over here, this regime over here. So that's a case where people have been sort of working a little on this side as well as this side, and they've kind of met in the middle. But it uses these very special properties of integrability, and we still don't have an idea of how general they are, how wide they are there even in some ways. So that's maybe one way in which one could, and I hope that we will be able to get a better idea of the reason for integrability, and that may be some way in which you can push things to intermediate coupling, to this order one coupling over here.
Rajesh,
Okay.
this the fact that the perturbative corner is sort of smoothly connected to the intermediate corner and not maybe separated by some boundary wall, is that an assumption, or is there some regular some good reason to expect that there wouldn't be any such boundary wall?
Yeah, so no, that's a very good question. I think there's no wall in the sense of a transition, but what I think does happen is that there is a radius of convergence of the perturbative expansion, and I think even in n equals to 4 Yang-Mills from integrability, it is known that there is this radius is around minus pi square. So in some sense, it is radius is pi square, but in lambda, but there's a kind of a singularity on the negative axis. So so of lambda. So lambda equals to minus pi square. There is a singular. So I think since Toft, one has known that the planar limit can have a finite radius of convergence because it's more like a geometric series rather than a Borel series. I mean, rather than some asymptotic Borel summable series. So so it's the planar diagram growth leads to a finite radius of convergence, but you can kind of analytically continue. So it's like 1 over 1 minus x. You can, if you write a power series expansion, it converges for x less than 1, or better still 1 over 1 plus x. So it has a finite radius of convergence, but it is well defined. You can analytically continue it to say. So I believe that's how, at least all the available evidence for the case of n equals to 4 Yang-Mills suggests that that's the picture, that there is a finite radius of convergence, but one can analytically continue.
Thank you.
Any other questions and so on about this sort of more philosophical part?
Rajesh?
Yeah.
There are other so there are other kind like there are field theory dualities as well, like for example,
right,
can you hear me? Hello? There are also field theory dualities, like,
correct.
so for them, what would be the goal, like finding out a duality invariant field theory, or like what's like the proving of the duality there?
So you could ask, even for n equals to 4 Yang-Mills, there is a strong weak coupling duality where the G Yang-Mills, roughly speaking, goes to 1 over G Yang-Mills. So there, in fact, I think those dualities are more difficult to prove. And at the moment, at least, I think they are more out of our reach. Because they are, of course, we have a lot of evidence for their when they are true, but we don't have a way to. I think our understanding of the framework of quantum field theory is probably incomplete, or at least we don't have a way to really show these non-perturbative dualities in quantum field theory. Whereas here it's slightly different, and that's why it's good that you brought up this point. As long as we are in the planar limit, in some sense, it is not a real, I mean, in the string theory side is not quantum at all. It's a classical string theory, which is described by a sigma model. And there's, of course, if you are working in this regime, if you are working in this regime, the field theory is also perturbative. So you might expect in this region, you can, it's more easy to think of actually proving it, because there are two well-defined frameworks which in principle you can control, namely a two-dimensional sigma model, which for the a dual AdS 5 times S5 at the classical level, and perturbative quantum field theory of n equals to 4 Yang-Mills, which you also know how to describe in terms of Feynman diagrams and conventional perturbation expansion. So it is potentially feasible that there you can actually match these two things, because they're both things which are in a way under your control. Whereas strong coupling Yang-Mills theory and relating that to weak coupling Yang-Mills theory, we still don't know how we could try to even try to prove that. So that's, I think, in the levels of difficulty of proving dualities, I think the AdS CFT is in some sense the easiest. And in some ways it is probably also one of the most interesting ones. But I think there is the next one would be gauge theory dualities in 4 dimensions. We have learned how to prove dualities in 2-dimensional quantum field theories, but I think we need a new idea if we have to try to prove dualities in 4-dimensional quantum field theories. And finally, I think there is string duality, which is, I think, quite a bit out of reach right now, because we don't even have a full non-perturbative definition of string theory. So, so in some ways, this is a bit like a weak coupling duality. So that's why this is, I feel this is more tractable or feasible. Does that answer your question?
Yeah. Okay, thank you.
Okay. So in some sense, the next point that I was going to make has been already sort of answered, which is how can we try to derive AdS CFT, and the short answer I want to say is that by starting at lambda equals to 0, this is the free gauge theory. So from the field theory side, this is something which is easy to understand, though I must say that even though we think that we understand perturbative quantum field theory well, I just want to add as a caveat that there are many remarkable features of perturbative Yang-Mills that people have been uncovering in the last few decades, which show that there is, even in perturbative Yang-Mills theory, there are things we don't fully understand. For instance, this hidden structure of scattering amplitudes and the dual conformal symmetries, in fact, even an intricate mathematics of scattering of Feynman diagrams. There's several aspects that I think still the integrability, etc. So the fact that there is a higher spin symmetry, how much does that control the free theory or the perturbative theory, which is broken? So all these are things there are still many. So what I mean to say is that free or perturbative Yang-Mills theory is not some boring corner of the parameter space. There are lots of interesting things happening over there, but at least we have a handle to understanding them. And there is, and what I will be focusing on is just a conventional textbook quantum field theory prescription for computing observables like correlation functions. So those are things we think we understand well. And so that side of the correspondence is something we know, this perturbative QFT part. But this corresponds to what you might call the tensionless limit of the dual string theory. This is sometimes it's called the tensionless limit because this RADS by the string length, which is the dimensionless quantity, this is the radius of ADS, the radius of curvature. This is, if you wish, I mean, the 't Hooft coupling is some function of this. So when you say that the 't Hooft coupling is going to 0, in some sense, the radius is going to 0, though perhaps what it really goes to is some minimal length, some stringy length. And so we'll work in this regime, and also, of course, 1 over n, which is G string, is also going to 0, so in the planar regime. So we have to just consider the sigma model in this regime. This is still non-trivial because we don't have people have been struggling to quantize string theory on ADS 5 times S5. But this is where I feel we can potentially make progress. And the proposal in the second part of these talks on the string dual for free n equals to 4 Young-Mills is in along such lines. It's a proposal that there may be actually this thing. And in fact, because the dual theory is a free theory, you might even might hope that the dual sigma model is also a free theory. There's no kind of rational reason for this, but the kind of proposal that we make is also along, it seems to be along these lines. So so one hopes that here we can kind of make a direct connection between the space-time CFT and the worldsheet CFT, the two-dimensional CFT, and make this connection manifest. So that's the hope. And also I want to add it, I just mentioned it briefly, but the enhanced symmetries at this point, the higher spin symmetries also suggest that this is a good point to expand around. So you might think that lambda equals to 0 is some kind of unbroken phase of symmetries of the string theory. And this has been an old idea going back to Gross and others, that the tensionless limit is where you might expect to see string theory in an unbroken phase. And when you go away from that, that's like Higgsing this symmetry. And just as we know in the Young-Mills theories or standard model, that in some ways all the symmetries are manifest in the unbroken phase. And that's where one should really start looking at the theory around, because it's much more difficult to do to understand the dynamics in the broken phase without understanding it in the unbroken phase. So that's one reason also why this might be a good point to expand around. So this was all sort of motivation for why this lambda equals to 0. This other lamppost might be a point to start expanding around and try to break out of these limitations that we had, the two limitations that I mentioned, both of understanding how general it is, because after all, perturbation theories holds for any field theory which has a marginal parameter, and similarly the limit. So we can try to see how general the correspondence is, and similarly by expanding around lambda equals to 0, we are definitely breaking out of that other box that we were in, and maybe this one will help us to push things further in some ways. So that's the hope. Okay, so that was the how and why. So are there any questions before I start on the next part, which is now to try to elaborate a bit more on this broad strategy by talking about how string theories can potentially trying to understand a little better what might be behind this mechanism of gauge string duality. So, so in some ways we are progressing now onto the how question in more detail. I think I spent a lot of time on the why question, why it is important to understand derive AdS CFT, but this is more the other part. Okay, so as I said, the question is, how does gauge string duality arise? And so short answer is open closed string duality. So this is the underlying reason ultimately for gauge string duality. So that's sort of, if you want to encapsulate it in a phrase, that's what it is. But that of course hides many things. So let's try to flesh this picture out, flesh this in some ways, this open closed string duality through some pictures and develop some idea for why, and that is the underlying reason. So first thing is recall, you might have seen in Polchinski's book and so on, that the simplest open closed string dualities are where you just look at a string worldsheet in just two different ways. And you might have seen this in many places, that so if I have a string worldsheet which is like that of a cylinder, then, well, on one hand you can think of this as like a, at least it's conformally equivalent, especially if you consider a long cylinder, it's conformally equivalent to sort of to closed string vertex operators inserted on a sphere. So you can, these two disks, if you wish, but on the other hand, you can also interpret this as an annulus diagram, which is a so annulus open string diagram. So here you think of a closed string propagating along this line, whereas here you think of an open string propagating in a loop here. So similarly, I could think of another, I could consider a 3-point function, which would be something like the usual Pans diagram. And this would be related to a disk with 2 holes. So totally 3 boundaries. And so you can interpret the same diagram, worldsheet diagram, in sort of either as some kind of tree-level closed string diagrams, or equivalently as loop diagrams of open string theory. And in this form, this relation between open and closed string, in particular, the first equality over here was behind, was what underlies Polchinski's famous derivation of the tension of D branes. Because he realized that you could view this as sort of a closed string exchange between two D branes at these boundaries, and you could think of it as a closed string exchange, but at the same from this open string point of view, you could think of it as an open string one loop diagram. And by computing this open string one loop diagram, he realized what the closed string exchange was, and he could read off the and this was more something like a gravity or closed string propagator in the lowest mode, and you could read off the tension which created the closed string interaction. Okay, so this is of course the simplest form of the open string duality, and Maldesena's proposal was a sort of a more sophisticated version of this. Maldesena's original proposal.
Sorry.
Yeah.
So that open closed string duality, it's true perturbativity, right? I can show it perturbative both sides, right?
Yeah. Yeah.
So whereas the gauge string dualities, there's a strong weak coupling involved, right? So why, how you are thinking this to be?
Yeah, so that's what I'm coming to. So just ask me if I'm not, I don't answer your question. Yeah, so just ask me a little later. So what I was in fact going to say was that is a more sophisticated version of this. Or in some ways, even an extrapolated version of this open closed string duality. And it also rested on the same sort of thing which Polchinski exploited. It rests on the two different descriptions of D branes. So ultimately, that's how, so one is the closed string description, if you wish. So the closed description is that D branes have a tension, as we just discussed, and hence back react on the geometry. And there is a, are described by, and are described by supergravity solutions in the appropriate regime. And these were the solutions that were discussed even before D branes were invented, these so-called P branes. And you can think of them as some kind of, so if I look at the transverse direction, this is sort of a P brane, so I'm not showing the extended direction. So the geometry around it, it curves the geometry around it. So there's some curved space-time around it. So so there's a, so that's the close string description, which sort of generalizes this this picture over here. And then there is also an open string description. And this is that d-branes can also be described as in terms of open, but more generally open plus closed strings, string excitations on a Dirichlet kind of a defect. In flat space. So you just start with flat space and you just consider this sort of a stack of these defects. So for the case of, say, some extended branes, and there are all these open strings and stretch between them, and then there are the closed strings in the flat space. So this is in flat space, you have these defects and these open strings stretch between them. So you have these two apparently different descriptions for the same object in the theory. So I think the real brilliant insight of Maldacena was that by taking a low energy limit, kind of a suitable low energy limit, is kind of a scaling limit, one can decouple the asymptotic closed strings from the open strings in this second description. So all these asymptotic closed strings that are there, in an appropriate low energy limit, the Newton's constant, which the Newton's constant times energy is effectively energy to appropriate power, is the dimensionless quantity, and which governs the interaction between the closed strings and the open strings. And these asymptotic closed strings get decoupled, and furthermore, you only have you also only have the lowest open string excitations. Open string excitations, namely the Yang-Mills. In the case of and I mostly focus on this for D3 branes, just for concrete illustration, and because that's the case that we will be mostly focusing on. But on the other hand, when you take the scaling limit in the first description, this scaling limit also decouples the asymptotic strings because the closed strings, asymptotic closed strings, so the idea is that in this picture here, there are also faraway closed strings, but here there are also closed strings in the vicinity of the horizon. So from the near horizon excitations. So and the close string excitations. So in some ways, what we have is basically saying that, so the picture one was essentially telling us that there are the asymptotic close strings, and then there are the near horizon close strings. That was the close string picture. And the picture two was saying there are asymptotic close strings and plus the lowest open string excitations. Wait, there are all the mass, okay, and then there are the massive excitations of the close strings also, but okay, let me just write here as just the open string excitations. Just so this is what we had, and these two pictures, of course, consistency of string theory demands that these two pictures must be the same. And in fact, in the scaling limit, so in the scaling limit, you get a useful statement, namely the near horizon in AdS 5 times S5 for D3 branes. And this near horizon close strings correspond to lowest. So here also you take this scaling low energy limit. So lowest open string. Which is equal to n equals to 4. So, so that was the statement that the consistency of the string theory of this open string picture with the closed string picture demands the equality of both of these things. So though this was this sort of derivation or argument for the open closed string duality is really valid only when the supergravity solution, because I mean, that's when you can really talk reliably about the first side in terms of this decoupling, etc. So though this is really valid only in that supergravity regime, which corresponds to the Yang-Mills coupling being very large, and in fact, that's you take that limit of the geometry, and when you do the scaling limit, you do take that limit in the geometry to to get the equality between the AdS 5 times S5 and the open string. So one extrapolates to all lambda. And that's what this thing, I mean, that's the statement, at least in this particular case, that closed strings on AdS 5 times S5 correspond to n equals to 4 superangles. And the parameters here, this RADS is something, the dictionary is that something like lambda to the 1/4, where lambda is the Stoft coupling, which I mentioned earlier, and G string is like 1/n. So that's the other parameter. So n, which is going to infinity. Yeah. So that we neglect also quantum stringy effects in this and work in a 1/n expansion. So so if you have not seen this derivation, you should look at, for example, section, especially for the younger people, section 3 of in this big review, very old review, but it still has this physical picture, very and elaborated more than I have done justice to here in terms of the near horizon excitations and the asymptotic excitations and why they decouple, because there's a potential barrier between them, etc. So, so I would urge you to look at this this thing. So, any questions about this? So, okay, so so let me try to draw the analog of the, so in a way, trying to answer Arnab's question earlier. So at least the heuristic picture here at least for large lambda, which is where is and also we'll also fix the number of handles G in the genus expansion. So the idea is somehow that in this genus expansion, we sum over holes, and it's this picture that I had in this cat picture. So so you have this cat, and these are open string vertex operators. I haven't drawn a very good cat, but anyway, yeah, this a little bit. So the idea is that when you sum over all the holes in this open string, I can also draw more open strings here, that this is equal to so the cat with only the whiskers and the smile and everything has disappeared. So this is some different version of the Cheshire Cat story. So the idea is that D3 branes here, this is the open string picture, that D3 branes in flat space and now go over to a close, this, when you sum over all the holes, which is what you would do at large lambda, you have many open string diagrams all contributing, and somehow the sum over all the holes This is or faces of the open string. And in the original D3 brane theory in flat space, that gives you somehow magically this closed string background. The large number of holes lead to a back reaction and the geometry and deform the background. From flat space to AdS 5 times S5. So, so this is this thing, and what would have been some open string, and we'll talk about correlators later, but open string vertex operators somehow go to closed string vertex operators. But so this is very schematic, but so there are punctures corresponding to this closed string. And this thing. So this is the picture, which is different from the picture we had over here in some ways, because it's here. I mean, I didn't say it explicitly, but it was understood that this is, when I say this is the same background, and let's say flat space. At least that's what we normally consider. We are looking at just the string theories on the same background, but here you are kind of summing over all of them, and in the process replacing them by a deformed background. And this is what I think Arnab was saying, that you have a strong weak coupling duality. So there is a this is the picture at large lambda in some ways, that it's not perturbative from the point of view of the gauge theory, why this equality happens. So this is a way to kind of give a picture for this Maldaceno's original proposal. Is this does this make sense?
So also in the left-hand side, you only mean the massless sector, isn't it? I mean,
yeah. So in this near horizon regime, so this is this open string picture is really the gauge theory picture. So D3 branes which go to the lowest excitations. So that's part of the somehow. This is just a this is not obvious at all that why this is true, but it is just a restating of the proposal in some pictorial way.
And to understand this a little more quantitatively, the number of holes is like n, capital N, and is G string times n.
Yeah, so actually, let me say that. So what do we mean by the left-hand side a little bit more? So imagine we are doing the Toft counting. So Toft counting on the gauge theory side. What do we do in the Toft counting? Remember, so this is, let me, this is a kind of an aside. So in the gauge theory, we have a Yang-Mills action, which we would write as n over lambda, some dx, and times the Lagrangian. And so this is so I've normalized the action such that 1 over g Yang-Mills square comes outside. Which if I write in terms of the Toft coupling, and n is just n over lambda. So that's why I've written this prefactor. So the Toft coupling, this means that if I have a Feynman diagram, So this was the original Toft counting, that Feynman diagram with E edges, V vertices, and F loops or faces. Comes with a factor which is the following. So each edge corresponds to a propagator. Propagator comes from the inverse of the quadratic term in the inverse of the quadratic term in the Lagrangian. So the inverse of the quadratic term will have a factor of n over lambda to the power -1. So you get a factor of n over lambda to the power -e. Sorry, there's a sound of the train. And then for every vertex, the vertices come from say the cubic and quartic or whatever interaction terms you have in this Lagrangian. So those are proportional to n over lambda. So you get a factor of n over lambda for each vertex. So you get a factor of plus v if you have v vertices. And finally, the loops are basically the color loops. So you get a factor of n to the f, because each face gives you this. So if you write it in terms of the use Euler's remarkable formula, you get v minus e plus f is 2 minus 2g. But I will write this as so there's v minus e plus f is the factor of n, but I can write this as lambda to the f if I write in terms of 2 minus 2g. So I'm using the formula. So this is of course the famous Toft scaling, and so what I had in mind, so this we close. So another way to think of the sum is to say you sum over all the holes, which is sum over f, and we are fixing the number of handles, so I can take out that piece n over lambda to the 2 minus 2g, and then there'll be some I should maybe, okay, I'll use f equals to n equals to the number of holes. So I'll write it like this, lambda to the n. So the sum is now over n. So this is the number of holes or faces. So there'll be some coefficients which we have, of course, the large n counting doesn't tell you. So I have, this is at least in perturbation theory, what it is would be like. So you would imagine that, like I said earlier, it has probably some finite radius of convergence. So you have some analytic function, which then you can think of for all lambda. And the statement is that it is this sum, it is this function, which is this is the closed string amplitude. The dual AdS 5 times. And so, yeah, so you have to sum over, in general, this is the sort of thing, this would be a little more the heuristic way of capturing that sum. Does that make sense?
Yeah, I was just trying to understand a bit more physically why you said use the words that summing over a large number of holes is going to lead to a back reaction. So it's almost like each diagram is associated with some kind of energy, and then that actually back reacts to give you a flow string background. So in what sense can we make this more precise?
Yeah, so and I'll sort of say this a little more, but yeah, actually I may not say it in this way. So it's good you asked. So it's in the following sense. You should think of each of these holes here as some kind of D-brane boundary state. And you will be essentially replacing each of these D-brane boundary states by closed string vertex operator insertions. And when you sum over them, that's essentially, it's like exponentiating insertions of these closed string vertex operators, and that is what deforms the background in some ways. It's a bit like starting with a sigma model in flat space, and you do an infinite sum over vertex operators which correspond to a graviton deformation, and by the time you have summed an infinite number of them, it exponentiates and deforms the background by a finite amount. So this is the analog of that. Okay.
So
any other?
How important are the non-perturbative corrections in going from left-hand side to right-hand side?
So when you say non-perturbative, you mean non-perturbative?
No. I mean, in this largen thing, you are doing the left-hand side. I mean, if you go down, if you are doing some largen counting, and then you said it can be rearranged to closed string amplitude in the dual AdS5 process, right?
Yes.
If I just restrict to perturbation series, can this rearrangement happen, or non-perturbative series, non-perturbative terms in both sides will come into play to make this rearrangement?
No, that's the nice thing, and this is related to, I think, the question, I think, when I was responding to Sachin, that you don't need the non-perturbative effects here, because these are purely open string diagrams. They are not they are perturbative open string diagrams. There are an infinite number of them, but you have to just sum them up. This thing, any non-perturbative effect in the gauge theory, for instance. So here in the closed string side, we are putting G string very small. So and we are looking at only terms which go like G string to the 2G minus 2. So on the closed string side, we are only matching things with finite number of handles like this. Any term which is, for instance, let me write it here, any term which has, say, d instantons or something, e to the minus 1 over gs, that is like e to the minus 1 over g Yang-Mills square. They're like Yang-Mills instantons, which go like e to the minus n over lambda. So these are exponentially small compared to this. In the large n limit, these are terms that you don't consider. You only consider, that's the nice thing, you only need to consider the terms which go like n to the 2 minus 2g. You don't need the you don't need to worry about terms like this. Okay, so so that's this thing that so this is what makes it very tangible, I think, that one should and that this is a case which one should be able to understand more precisely. So we are almost at the 4:30 mark, but I'll just shall I take 5 more minutes or so?
Sure. Yeah, it's fine.
Yeah, I'll just finish I want to close with this section this time. So so this is, I was trying to give a picture of the Maldacena strong coupling derivation, but in a way, as I said, our interest is in the opposite limit. So starting with lambda equal to 0 and near 0. And so in fact, I claim that there's a simpler picture of open closed string duality. This, which is closer to the original original one that I started off by drawing. So what I want to claim is that each open string diagram so in the original case, what did we have? We have each open string diagram corresponds to a closed string diagram. With the boundary being replaced by a closed string insertion. So what I want to claim is that this diagram with the is slightly modified. Now we'll consider in this case a D brane in AdS 5 times S5 at 0 radius, so to say. And we want to claim that that's so each of these is now a closed string insertion. And so with closed string insertion. So that so at in any fixed background, that was the original picture, that you kind of replace the D brane boundary states by closed string insertions. That was the heart of the original picture that I was drawing over here. There, of course, the background was the same. You're just considering two different ways of writing the same thing. And at lambda equals to 0, this this is what I claim is really happening at lambda equals to 0. Firstly, because there are we don't have to sum over infinite number of holes or anything at lambda equals to 0. And let's say we are firstly, strictly speaking, at lambda equals to 0. Then there's only a finite number of Feynman diagrams. And I want to claim that those diagrams are in correspondence with closed string insertions. So in some ways, we haven't, at lambda equals to 0, we haven't even exponentiated things. We are really considering some open string picture. But now the question is that presumably you want to know whether this is equal to also super Yang-Mills, n equals to 4 super Yang-Mills at lambda equals to 0. So picture is slightly different, and are equivalently, if you start from the right-hand side, you can ask, how do the holes open up in a closed string picture of AdS 5 times S5? Because the claim is that somehow you can think of a closed string correlator in AdS 5 times S5 also as a Yang-Mills correlator, which is some kind of presumably some kind of a D-brane background in that highly curved AdS 5 times S5. So this might sound that we have kind of and these two pictures are continuously connected to each other. You would expect that it is the sum over these holes should be somehow, when you sum over the holes, that's just another way, whether you consider D3 branes, whether they're excited in flat space or in AdS 5 times S5, it shouldn't really matter. In the end, it is just the open string excitations which you see, which are just the n equals to 4 super Yang-Mills excitations. So, so that's so this is the picture that one might have at V-coupling, and then the question is, can we see these, or can we realize this kind of open closed string duality in around this small radius? And there is actually an example, and I won't probably go into it in detail, but I mentioned this in my strings talk. Also, there's this duality between Chern-Simons theories at large N and dual topological closed string theories, which we had proposed with Wafa long ago. And there we had made a proposal for a mechanism by which these holes open up. And this was elaborated on in the paper of Oguri and Wafa, which which talked about a world sheet gauge linear sigma model, and how there are two phases in that sigma model, and there is a Higgs phase and a Coulomb phase, and actually the Coulomb phase nucleates the holes, and that's how in some ways the holes open up on the closed string world sheet. Maybe right now I don't want to get into that because that will be going quite far afield, but later, maybe towards the end of my lectures, when I talk about the n equals to 4 Yang-Mills, where in some ways we see a very similar picture arising, then maybe I'll say more about it, and anyone who is interested can ask me about it at that time. But what I wanted to say is that there is a proposed way, there is a mechanism by which I think this happens, and we see it in this toy model of Chern-Simons theory, the Chern-Simons duality, and we see indications that this is actually holds also in the proposals that we have for AdS 3 times S3 and AdS 5 times S5. But so we'll postpone a more detailed discussion of that to next time. So next time I will make some general remarks now about the third point that I mentioned, and I'll spend a little time on that, about going from fields to strings. So that will be the topic of Friday's lecture, and so hopefully with these two lectures I would have finished part A of the my general plan, and next week we will start on the proposal for the n equals to 4 super Yang-Mills itself. So yeah, so thanks, and sorry for having gone over time. So any questions or?
Yeah, thanks very much, Rajesh. So just whoever is hanging around, just note that the next lecture is going to be on Friday, 23rd, again at 3 p.m., not Thursday. So we will send out a reminder email, of course. Yeah, so questions.
Hi, Rajesh. Thanks for the nice talk. I was curious about this left-hand picture that you have right now on the screen. So the radius of ADS is much smaller than the string length LS.
Well, that's a kind of yeah. We don't really know what to call that. I mean, I think there's some minimal length or something. I mean, that's why I put 0 radius in quotation marks. It could be of order string scale for all we know, because the notion of radius is, I think, a little difficult to define at that stage. But yeah, but in any case, maybe that's not directly relevant to your question.
No, my question was that in the case of ADS 3 times S 3 times T4 at k equals 1, the radius was very well defined in terms of the square root k times ls, and then the radius is actually equal to ls. But here I was a bit confused and that it goes to 0 and still you are saying that there is an ADS 5 cross S5 because it's completely stringy and this notion of radius is not very well defined. Maybe if you can explain this a bit. Maybe
yeah. So all I can say is that, well, in a way, what you define as the radius is a bit up to you. I mean, in some sense, in the ADS 5 times S5, yeah, there is a Weismann-Witten model. ADS 3 times S3, there's a Weismann-Witten model, and in the presence of 1 unit of NS flux, you can say, I mean, if you extrapolate this dictionary, so after all, our dictionary for the radius and everything is from the supergravity solution. And we are extrapolating it to small coupling, to small radius, which is, I don't think it's quite a valid extrapolation because it becomes stringy and the supergravity solution is corrected. So I think the best one can say S3 times S3 is that it's of order string scale. There, of course, one had a Weismann-Witten model, and there is a level, and you can say that that kind of defines the small radius. So that's the minimum value. Here in ADS 5 times S5, you're right that there is nothing analogous, so we don't really know. And even the dictionary, which I kind of wrote over here, that maybe somewhere I wrote about, yeah, this one, that it is like lambda to the 1/4. So it might seem as if it is going to 0. Even that's an extrapolation from the large radius ADS. So it's not very clear that that's you would really trust this relation only at large radius. So there may well be corrections, and there's probably some minimum stringy uncertainty length of order string scale. So the minimum radius is maybe 1 in some units, appropriate units. But yeah, but I don't have a good answer to that. So we just define it as whatever the dual geometry is corresponding to lambda equals to 0 in the gauge theory.
I see. So a more appropriate mathematical statement would be that you have a sigma model that's dual to n equals 4 super Young-Mills at weak coupling at lambda equals 0.
Coupling, yeah. So that's right. And in some sense, the proposal that we make is a kind of, again, a level 1 Weismann-Witten theory, but for now, for the supergroup PSU 2,2/4, since you're familiar with this thing, I thought I'll mention that. So there also, there is a level which is odd, which is 1. So that's at least our proposal.
Okay, right. Thanks.
Any other questions?
Just a comment. I mean, there are other examples. In the original Maldacena duality, there are a couple of more examples. I mean, just for the students. There is the n equals 4 Young-Mills. Then there is the ADS 7 example. I mean, the ADS 4 times S7 example.
7, yeah.
The example and the
ABGM
model example and the D1, D5. I mean, just as a sort of the just indicates that there are a few more examples.
Yeah, so there are a few other, the same ADS 3 times S3 I will probably touch upon a little bit before I motivate the ADS 5 times
Rajesh,
S5 case.
I lost you guys.
But the others I won't, in principle, I think you could try to address the ABJM case where there is also a weak coupling. I hadn't thought about it hard enough. The ADS 7 times S4 case is more tricky because it corresponds to an isolated CFT, which doesn't have a weak coupling limit as we know it. So it's a isolated fixed point, strongly coupled CFT, and its dual is M theory, and so there's no real stringy dual. So I don't have any good idea about that case and how one would try to prove it or anything. So I'm assuming in some sense everything that I said today is in the context where we have two parameters. There is not only 1 over n, which sets the quantum scale, but also this other lambda, which you can tune to weak coupling in the field theory. And of course, very highly curved sigma model on the dual side. So there is, so you need at least 2 parameters or 1 more parameter in addition to large n. So that's the class of examples that I'm considering. And of course, since Maldacena, there have been many others. In fact, ADS 5 times, there are these so-called YPQ or there are YLMN, or there are
YPQ, yeah.
YPQ, and then there is a more general TLMN or something. There's a larger family of these, and some of them, I mean, for the YPQ, I think there's a candidate set of dual CFTs. So there are, people have generalized to many more cases, but typically with a high amount of supersymmetry. And then there are things which have RG flows between different sigma models, etc. So yeah, there's by now a fairly large class of examples, but I will focus on this most canonical one.
Thanks.
Yeah.
Any other questions? Okay, so if not, let's thank Rajesh for a very nice talk, and we will reconvene on 23rd at 3 p.m. I will pause the recording.